Stanford University.
The last time we discussed both the classical, I think, and the quantum mechanical description of harmonic oscillators. And we found classically that every harmonic oscillator has an energy which is independent of its frequency and equal to the temperature in thermal equilibrium. We calculated the partition function, and we calculated the average energy of any harmonic oscillator and found out that the energy was just equal to T. When I say T, it would be the textbook KT equals what I call temperature. All right, that's a true statement. It led to this puzzle about molecules which have little oscillators. How come in at very low temperatures also the molecules don't exhibit this energy? Because it's not there. We know that the molecule will not exhibit internal energy at very low temperatures. And we found out that the answer had to do with quantum mechanics. Instead of the energy being equal to T in quantum mechanics, we found out, well, let's just go through it. I'll go through it very briefly. There's some points here that are worth emphasizing. The energy levels of the quantum mechanical oscillator are E sub n equals h bar omega n. We can drop this ground state energy, it's not important, or put it in. It doesn't matter, it won't make any difference to anything. Incidentally, there's an interesting point here. The uncertainty principle is a correct principle, but you can think of it a little more broadly. Any given quantum state always corresponds. Now, I'm using the word correspond loosely, and I'm not going to tell you precisely what it means, but it corresponds to a little patch in phase space, x and p. It corresponds to a little patch in phase space where the area of that patch is equal to Planck's constant, and maybe it's Planck's constant over 2, I don't remember offhand. And it's not a question of greater than or equal to, it is equal, any given quantum state, to a patch of size h bar, of area in the phase space equal to h bar. Now, if the area is a little circle, that's sort of the most tightly knit kind of quantum state, then of course, a little circle in phase space, then clearly delta x and delta p will be equal to each other, and delta x, delta p will equal h bar, will be proportional to h bar. If the size of the area of the circle is of order h bar, and I'll use the term of order h bar, then if we take a nice little symmetric disk like this, then delta x times delta p will be equal to h bar. There are other quantum states which have the same area, which might look like ellipses. Again, for an ellipse like this, if delta x times delta p is equal to h bar, or if the area of this patch is equal to h bar, then again, delta x times delta p will be equal to h bar. But then there are much more peculiar states. There are states, quantum states, which correspond to the area h bar, but which are spread out in some other kind of way. Like that. The properties of the quantum state can be identified with a patch of phase space whose area is equal to h bar, but it's quite apparent for this kind of configuration, this snaky kind of configuration whose area is h bar, that delta p times delta x is really greater than h bar. Delta p means the spread in momentum. Delta x means the spread in x. And if you don't keep the configuration tightly knit into some circle or ellipse or rectangle or something like that, but let it get spread out into this kind of snaky configuration, then you can take a quantum state which occupies area h bar and nevertheless make it have delta x and delta p such that the product is greater than h bar. So it's kind of interesting, and I'm going to give you an example now. An example where this is useful in thinking. It's the harmonic oscillator. Let's just take the Hamiltonian to be p squared plus x squared over 2. I don't want to introduce any constants into here. It just makes it simpler. And the ground state is this wave function or this probability distribution which is concentrated at the center, and it has an area h bar. Delta x times delta p is h bar. Now what about the first excited state? The first excited state, if you think about a harmonic oscillators oscillate, and they oscillate in both momentum and position. And if you think about the way the phase point moves in phase space classically, it moves in circles. When the circle is projected onto the horizontal axis, you have the ordinary oscillation of position. When it's projected onto the vertical axis, you have the oscillation of the velocity or the momentum. The next excited state represents a harmonic oscillator with a little bit of increased energy moving around in a semi-classical and approximate classical description in a circle. And so it occupies a little ring of phase space. But how big is that ring, or how thick is that ring? That ring must be such that the area is again equal to h bar. The next excited state is another ring of area h bar. As you move out, the width, since the total area of each state is equal to h bar, as you move out further and further, the thickness or the thickness of the annular ring describing each quantum state does get thinner and thinner, but the area stays the same. What's the radius of the nth circle here? Anybody figure that out? If we take the nth circle, what? NH
bar is the area.
No, NH bar, yeah. NH bar is the area of, yeah, H bar is the area of the circle, of the annular ring. Okay.
Altogether, NH bar is the total area.
Yeah.
And then divide by the number.
Well, I'll tell you what the answer is. The answer, I believe, is the square root of n is the radius of the circle, the square root of n. Okay? So the radius of the circle here is the square root of n. Square root of the nth circle. Just fitting them together. Yeah, question? Is there a question?
Doesn't pi r squared have to be?
There's pi r squares, but again? No, we're just talking about the radius of an annular ring, the nth annular ring, such that each one butts up against the next one and gives you a disk of area n. Yeah, the area, this n such, we're talking about the nth ring. Each one has area h bar. So what is the area of the whole disk here? The whole area of the whole disk is proportional to n, but the area of the annular ring, all right, let's do it. The area of the whole disk is n. So the area n times h bar. I just want to figure out whether it's n to the 1/2, n to the 3/4, what it is. The area of the whole thing is n, yes, times h bar. That's the area of the whole thing. And that's equal to pi r squared, where r is the radius of this disk in phase space, right? Pi r squared. All right, so that tells us that n h bar over pi, the square root is equal to r. Now, what does that mean about the, oh, that does it, doesn't it? That tells us that the radius of the annular ring out here, the nth annular ring, is proportional to the square root of n. That's the important thing. It's proportional to the square root of n. In fact, it's proportional to the square root of n times h bar. Now, what is this radius? If you look at this formula over here, you see that this radius, or the square of the radius, is essentially the energy. The square of the radius, we can think of this as r squared, and it is just the energy, apart from a factor of 2. I'm being loose with factors of 2 and even with factors of pi. So p squared plus x squared is the energy, and that's equal to r squared. R is of order nh bar, so that means that the energy is of order... No. R squared is just of order nh bar. So the quantization of energy can be just thought of as the uncertainty principle for the case of the harmonic oscillator, but the uncertainty principle not thought of as delta E, delta P greater than h bar, but a different kind of uncertainty principle which tells you that every quantum state occupies a little region of phase space which is of order h bar in area, but that doesn't mean that the shape has to be a little circle. In this case, the shape is annular rings. The uncertainty of these of delta x times delta p of these excited states is much bigger than h bar. If I take this nth excited state here and ask what is its delta x and its delta p, they're this big and that big, and it's much bigger than h bar. So that's a useful way to think about quantum mechanics, that quantum states are to be identified as patches of phase space whose area is h bar. Each one of these is a unique quantum state, distinguishable, discrete, and so in any one of these states, no matter how big delta x and delta p get, every single one of them is a unique, definite quantum state. And if you know that the system is in that discrete quantum state, then the probability distribution in quantum states is just localized at one unique quantum state, and the entropy is 0. Okay. In thermal equilibrium, of course, these different rings have a probability distribution, and it's the Boltzmann distribution, and the entropy is whatever it is. All right, so I got sidetracked into an interesting discussion, but let's go back to the classical and the quantum mechanical harmonic oscillator. The classical harmonic oscillator up in the left-hand corner has energy E equals T. The quantum mechanical oscillator, did we write down the answer? Okay, let's write down the answer. The energy of the quantum mechanical oscillator is omega h bar. Oh, let's just go through again where it came from very quickly. We calculated the partition function. The partition function came from summing up over all the quantum states, which means summing up over all those annular rings, e to the minus beta. We start with the partition function, e to the minus beta times the energy of the nth level, which is h bar omega times n. That's a geometric sum. Let me just very quickly go through it. Sum, that's equal to 1 over 1 minus e to the minus beta h bar omega, or equal to e to the, that's good enough. That's a good way to express it. Okay. And then from that, we can calculate the energy of the oscillator. This is z. Log z we can calculate. Log z is just a logarithm of this, and we can calculate the derivative of minus log z with respect to beta. That's the energy, average energy, of course, of the oscillator. And that's equal to omega h bar divided by e to the beta omega h bar minus 1. The 1 coming from the 1, you see what it is. All right, so that's the energy. And if you look at it and stare at it for a minute, you realize that at high temperature, when beta is small, we can expand this exponential. It becomes 1 plus beta omega h bar in the denominator, minus 1 omega h bar. And 1 minus 1 cancels. Omega h bar cancels. And the answer is 1 over beta, which is temperature. So at high temperatures, we reproduce the classical physics. But at low temperature, when beta is very large, when temperatures are low, beta is large. This exponent here is very large. You can forget the 1, and the energy is just omega h bar over e to the beta omega h bar. And that's extremely small. When beta is large, temperature is small, the energy is tremendously suppressed compared to the classical answer. So that's the solution, if you like, of the puzzle of what happens to the classical energy stored at very, very low temperatures. It's much less than you would have gotten from classical physics. At high temperatures, they're the same. At low temperatures, it's very hard to excite the oscillations, basically. All right, one other thing. The n which appears here, we can just define. By definition, we will call it the number of quanta in that oscillator. We'll think of the oscillator as having an occupation number, whatever that means. Just definition. The occupation number of the harmonic oscillator is just which of these rings you're on, or which quantum state, in the sense of how many units of energy does the quantum state have, units of energy in units of h bar omega. So that's, if you like, a definition of the number of quanta in that oscillation. The next thing we're going to come to is blackbody radiation. Blackbody radiation is of enormous historical importance. And of course, it's also of importance in many, many other ways besides history. But it has a glorious history in being the origin of quantum mechanics, or the historical, yeah.
Was this thought of as a paradox?
Which?
The fact that the classical result of the energy being equal to the temperature?
Yes. Yes, but it wasn't. It was.
I'm wondering, it could have been interpreted as a need for other physics at one time.
Okay. The answer is I don't know the degree to which people actually are worried about that. About the molecular, you talk about the molecular internal motions.
Right.
I'm quite certain that they did worry about it, but remember that they knew very little about molecules at that time. And the whole idea of molecules had yet to be really established. So my own guess is that, yes, they knew about it, they worried about it, but it wasn't in the front burner the way that the blackbody radiation was. Radiation, they thought they knew everything about. Wave theory, electric and magnetic fields. They thought they really understood electromagnetism. And the puzzle, which was very similar, a very, very similar type, was that a box of radiation, by a box of radiation, I mean we take some cavity, I guess we would call it, with reflecting walls. Now, of course, we don't have perfectly reflecting walls. It doesn't matter much. In fact, it's even better if they're not perfectly reflecting, but they transmit some energy through them. Then we can say that whatever's in the box will come to a thermal equilibrium on the outside, with the outside at a given temperature. But what can be in the box radiation can be in the box. Radiation bouncing back and forth, waves of radiation bouncing back and forth, radiation of different wavelengths. Now, it was known from very early times from Maxwell theory and so forth, that the radiation inside a box could be thought of as a collection of harmonic oscillators. In the same sense that a vibrating guitar string, I always mean to bring my guitar in for this purpose, but like a vibrating guitar string can also be thought of as a system of harmonic oscillators, not a single harmonic oscillator. Hey, that's pretty good. Not a single harmonic oscillator, but it can vibrate in any one of its, ooh. Yeah, you get the point. This is the first mode of oscillation, and that's a harmonic oscillator. Completely independent of that, the system can vibrate in its second mode. Now, I'm not going to try to make that, well, yeah, I can do the third mode. There's a third mode and so forth. And each one of these oscillations is separate, and the system is described by a collection of harmonic oscillations. Each harmonic oscillation, and this was not an invention of Einstein, or this goes back to original wave theory, everything we knew about wave theory, not everything we knew, everything they knew about wave theory, that waves could be described as collections of oscillators. And in thermal equilibrium, each oscillator ought, according to classical thermodynamics, have an energy equal to kT. But there's an infinite number of possible modes of oscillation. I could only exhibit a handful, because I'm not clever enough to make this thing oscillate in arbitrarily short wavelengths. But there was no reason to believe that there was any cutoff in how short wavelengths could be. There is a cutoff on how long wavelengths can be inside a box. It doesn't make sense to think about a wave longer in wavelength than the size of the box. Or another way of saying it is, if you have a guitar string of a certain length, there are not going to be waves of longer wavelength on that guitar string than the distance between the endpoints of the string, but there can be arbitrarily short wavelengths. Now, of course, for a real guitar string, it has a certain thickness, and there comes a point where you can't really make it oscillate with very, very short wavelengths. In particular, it doesn't make any sense to think about wavelengths shorter than the intermolecular spacing along So for a guitar string, there's a natural cutoff. But for radiation, nobody knew any reason why there should be a smallest wavelength. And if not, then in thermal equilibrium, every single wavelength should have the same energy, kT, and the damn thing should have an infinite explosive amount of energy, simply because there's an infinite number of possible ways you can oscillate. Of course, most of these wavelengths would be very, very high frequency, but nevertheless, thermal equilibrium should populate them. The same way the thermal equilibrium should have populated the oscillations of a very stiff molecule, it should also have populated the oscillations of a very stiff string, for example, very high frequency oscillations. So that was the real puzzle. And people knew enough about electromagnetism that they had confidence in the theory, and the theory was failing. It was failing because it was an observed fact that the radiation inside a box was not infinite in energy. In fact, if you looked at the radiation that was in the box, you would discover, in fact, that there was a cutoff in its wavelength. The cutoff, in other words, a shortest wavelength that the box could oscillate at. So you might have said, okay, that just means that physics has some smallest length. Right? We didn't expect that, something new, something entirely new, but still, it can be made to coexist with basic classical physics if we were to have said there was a smallest length. But it doesn't work that way. The smallest length wave or oscillation that's present in the thermal equilibrium of a box of radiation, that smallest wavelength depends on temperature. How can the shortest distance in the world depend on the temperature? That doesn't make sense. So when a box of radiation was considered and studied, and how do they do this? They let a little bit of radiation out and studied the spectral decomposition of it. At each temperature, there was a shortest wavelength, or approximately a shortest wavelength, but that shortest wavelength depended on something that it didn't make sense, that it depended on the temperature itself. That was the puzzle. The solution of the puzzle was simply the quantum mechanics of these harmonic oscillations. So I want to go through that and show you the basic theory of the harmonic of radiation, and we'll work out the Stefan-Boltzmann law, or one particular version of the Stefan-Boltzmann law. The Stefan-Boltzmann law applied to the energy density of radiation, blackbody radiation. We're talking about blackbody radiation. Okay, any questions before I begin this, the derivation of the energy in blackbody radiation? Yeah.
It seems like the minimum wavelength would be cut. Eventually, the wavelengths would get to be about the size of an atom, and that should cut off the minimum wavelength.
Why should it? Why?
Because
Why?
then it's not a perfectly reflecting wall, and it's just a jaggedy bunch of atoms.
No, in thermal equilibrium, everything gets populated. Everything gets populated that can get populated. And there's no reason why an atom cannot, in principle, or why an atom cannot excite modes of oscillation of yet shorter wavelength. It might take a long time. It might take a long time to populate. Atoms of a certain size aren't readily going to convert. I'll tell you what can happen. How can an atom create a high frequency photon? Okay. Well, one simple way that it can create a high frequency photon. We haven't talked about photons yet, but let's talk about photons. One way that it can do it is to absorb simultaneously several low frequency photons and then re-emit the energy as one high frequency photon. Okay? So it can happen. It's one of the possible processes that can happen, that an atom it's a nonlinear process. The frequency of the radiation changes, but a whole bunch of photons come together. You can think of it as accidentally excite the atom, and the atom then de-excites and gives back a very high frequency photon. Or scatters a lot of low frequency photons and creates a high frequency photon. They say that's very improbable, and you're right. That means that it would take a long amount of time for the system to come to thermal equilibrium. And that's true. That classically, it would take a long time for the system to come to thermal equilibrium. But when it did come to thermal equilibrium, it would have this odd property of having every mode filled with energy and an infinite amount of energy. And that was intolerable. But let me say it another way. At low temperatures, the cutoff in wavelengths was much longer than the size of an atom. Okay? So it didn't make sense to just say atomic diameters cut off things. It depended on the temperature. At low temperatures, only very long wavelengths were present. As the temperature went up, shorter and shorter wavelengths become important. And this just didn't jibe with anything that anybody knew. I mean, it was a real crisis. Planck had an idea, and the idea didn't really make a lot of sense. I will just tell you very briefly. It's one of these things that made sufficiently little sense that I can't even reproduce what the argument was. It was Einstein, of course, who really got the argument right. What Planck said is that the walls of the container are filled with atoms. Atoms emit radiation. And for reasons he didn't know, but reasons that didn't seem all that incredibly revolutionary, the oscillators in the walls oscillate only with very definite frequencies. All right? And he said the energy of an oscillator, he spoke about oscillators in the walls of the system, meaning atoms. But again, remember, this was 1900. Atoms still hadn't been identified and still were not understood. So Planck said, for reasons unknown, the frequency of oscillations of atoms, do atoms even oscillate? Not all atoms oscillate. I mean, they do oscillate, but they don't oscillate as harmonic oscillators. But his idea was atoms oscillate like harmonic oscillators. And each harmonic oscillator atom has a frequency omega. And he said the energy of the atoms, or the oscillators in the wall, satisfied that the energy is equal to an integer multiple of the frequency times a new constant, which he called, I don't think he called it Planck's constant, he called it h. He called it h bar, or h. H bar came a little bit later. H nu equals h bar omega. And through some kind of mumbo-jumbo that I've never completely understood, this was supposed to explain the fact that, that the radiation in the box was cut off at some highest wavelength. This is not the right explanation, although the formula that he concocted out of this was correct. The formula he concocted for the amount of radiation in each oscillator was correct, or in each oscillation of the electromagnetic field. The real truth was that the quantization of energy levels was not the quantization of energy levels of the atoms in the walls of the box. It was the quantization of the energy levels of the radiation itself inside the box. In other words, the radiation was made out of discrete quanta of energy, where every frequency of possible oscillation would have an integer number of quanta, and the energy of each possible oscillation would be some integer times h bar times the frequency of that oscillator. The thing that I've called quanta now, which just correspond to the amount of energy in each one of these oscillations, got to be called photons. Einstein knew very well that he was talking about some kind of particulate theory of radiation. And he was saying something extremely radical, extraordinarily radical. In fact, you know, it's when you think about it, there was this young man who was completely unknown. Nobody had ever heard of him. There were all these famous physicists. And this young man out of nowhere, out of the patent office in 1905 said, you know, everybody who has ever thought about radiation and electromagnetic radiation had it completely wrong. All you people were wrong. Electromagnetic radiation comes in some sort of particles. Now, it was not because he didn't understand that the wave theory of radiation was very effective. He just somehow had an inner sense that it was the radiation in here which was quantized and not the oscillations of the wall. Nobody believed him, incidentally. It took about 20 years before people really believed there were photons. Even this, it was a long time, but having told you the history, let's go through the mathematics. This is not what Einstein did. Einstein didn't have the mathematics to do this. He didn't do it the way I'm doing it. He did it using lots of thermodynamics and lots of clever insight. But we can do it really mathematically and very cleanly. All I want to do is calculate the total amount of energy in this box of radiation. So to do so, we have to state more clearly the nature of these oscillators, not the ones in the walls of the box, but the oscillations in the radiation field, which are very much like the oscillations of a guitar string. In particular, if the walls of the box are reflecting, that implies that the electric field at the boundaries of the box is zero. take that as given, that the electric field at the boundaries of the box is 0. And that's analogous to the guitar string where the deviation of the guitar string from equilibrium is 0 at the boundary of the string. Right? Electric field can be thought of as sort of the height of the oscillation here. And so the guitar string is constrained to be attached to have 0 oscillation at the ends of the guitar string. Same thing for the electromagnetic field, for the electric field. So let's think about an electric wave propagating along the x-axis here. What? Yeah.
This is an idealized box with walls that are not irregular and things like that.
Yeah, but actually that doesn't make any difference at all if you're deep inside the box. There are some surface effects at the boundaries of the box that...
But wouldn't it mean that there would be a lot of different frequencies? I mean, it'd be like having a whole lot of different guitar strings.
No. What is true... You're asking, if you were to expand the box a little bit, you would say the frequencies would be a little bit different, and if you would shrink it a little bit, they would be a little different.
If you reflected them a little bit towards one wall or another or something.
Yeah. What you have to do is you have to you don't just add those things together. You can't add the oscillations of one theory of the guitar string to the oscillations of another theory. For example, you could have, instead of fixed boundary conditions here in the guitar string, here's another kind of guitar string. It's not a real guitar string. You have a pole and another pole over here. Pole, I mean literally like a pole. And you have a ring around this pole and a ring around this pole, and the guitar string is connected to the rings. The rings can move up and down now. They're not confined to be attached to fixed positions. And this is an entirely different kind of waves. The waves that now can exist are such that they don't have to vanish at the endpoints. Something else has to be true, namely the derivative has to be equal to 0 at that point. But it's simply a different system. This system, if you worked it out, would give you exactly the same answer for the thermodynamics of the guitar string when the whole system got large. The end effects are not important. The end effects turn out not to be important. That you have to prove. You have to work that out. You don't add the oscillations of this theory to the oscillations of this theory. They're just two different theories. Now, another possibility is you could have friction at the end of the walls here. Friction would lead to yet a different description of what goes on in the guitar string, but all of them would lead to the same thermodynamic behavior of the guitar string. So it's sufficient just to study one particular case, and far from the endpoints, the answers don't depend on the details of the boundary conditions. I agree, that has to be proved. That's not obvious, but it's true. So let's consider the waves that can exist on a finite string of length L. If they have to vanish, if the height of this wave, let's call the height of the wave here, let's call it x. No, let's not call it x, let's call it capital Y. And it's a function of position, it's a function of x, and a given wave has to have the form sine pi, pi over Lx times n. What is n now? N is the number of oscillations, number of half oscillations. This would correspond to n equals 1. This would correspond to n equals 2, and so forth. Let me call it m. I don't want to call it n because I've used n for something else. I've used n for the number of quanta in the oscillation. This has nothing to do with the number of quanta in the oscillator. It just has to do with how many nodes there are in a particular electromagnetic wave. It's a completely classical concept. And it's just the kind of sine waves that can fit onto an interval of length L. All of these sine waves, okay, let's just look at it. If m is equal to 1, then this just becomes sine pi over L x. But what is x at the other end? X starts at 0 over here, and x is equal to L over here. At x equals 0, the sine of 0 is 0, and at x equals L, the sine of pi is 0. So this wave fits into the box with proper boundary conditions at the end. Any integer here will work. So there are an infinite number of patterns of oscillation characterized by these sine waves. But the sine waves, each one of them has an amplitude of oscillation, which means the magnitude of the oscillation of each one of these. And so you have to put a coefficient in front of it, y, let's call it sub m. And it's just a number for each oscillation, but it's time dependent. The oscillator oscillates up and down, or let's take this case here. It oscillates up and down, and that corresponds to y oscillating. Y is an oscillator. Y is a function of time, and it is an oscillator. It's a harmonic oscillator. So these are the oscillators here, and in general you can write that y of x is a sum over m of y sub m sine m pi over L x. These are the dynamical degrees of freedom. Think of this as a function of time. Y is also a function of time. And these are the things that oscillate. These are just fixed functions. So the system is a system of harmonic oscillators. And the next question is, what is the frequency of each oscillator? The answer depends on the velocity of propagation of the waves. There's a relationship between m and the frequency of oscillation, and I'll tell you what it is. Let's write this in another way, another useful way. Let's write this as y of m sine kx. M pi over L I have called k. That's a standard terminology. M pi over L is called k. And k is called the wave number. Okay? It's called the wave number. It's itself not necessarily an integer, but if you know m, then you know k. What's the connection between the frequency and k? The larger k is, the shorter the wavelength. That's large K, this is low k. Shorter the wavelength, the higher the frequency. I'll tell you what the relationship is. The frequency is equal to the velocity of propagation, let's call it c, times k. The higher k, the larger k, the higher the frequency, and they're just related by the velocity of propagation of waves. For light, c is of course the speed of light. All right, so let's summarize then. A given wave-like motion is parameterized by an m. It has a frequency which is equal to c times k, which is the same as c times m pi over L. Each one of these oscillations stores energy independently of all the others, and classically each one of them would store the same amount of energy and the whole thing would have an infinite amount of energy. Now, what about, now here I'm talking about one-dimensional waves. What about three-dimensional waves? Three-dimensional waves, you do almost exactly the same thing. Let's write the general pattern for three-dimensional waves. We're not now talking about the height of a string. We could be talking about a wave field such as the electric or magnetic field in a light wave. But let's not call it electric. Well, we can call it electric field. No, let's just call it F. It could be electric field, it could be magnetic field, or it could be some other wave field, gravitation. Well, no, let's not get into quantum gravity today. The electric or magnetic field. And it is also a sum over different independent oscillators. Now the wave pattern involves all three dimensions. And the general wave that can propagate in a box in three dimensions with boundary conditions on the walls that it should be zero looks similar to this, except it has three factors. It has sine. We can write it in several ways. M sub x, let's see, pi over L times x. It's a product, times sine m sub y, pi over L times y. Times sine of m sub z, pi over L times z. These are the three directions of space, and mx, my, and mz are integers. Three integers. A given wave has to fit into the box horizontally, it has to fit into the box vertically, and it has to fit into the box in the other direction. And that's ensured by this form here. And then there's a coefficient which depends on time, which can be labeled y of, or y sub m, meaning y of mx, my, and mz. We can also write this. Oh, and this is a sum, of course. We sum over all possible modes in the box. Right. And of course, this is nothing but Fourier analysis in a box. There's nothing special here. We can also write this as a sum of y and use a different notation, sine kx times x, sine ky times y, sine kz times z, where the relationship between the k's and the m's is exactly as it was before. K sub x is equal to m sub x pi, k sub y is equal to over L, and so forth. All right, this is the pattern of oscillation of a general electromagnetic wave inside a cavity, with y being the thing that oscillates. The point is that there is one harmonic oscillator for each way of choosing mx, my, and mz, and we have to add together all of their energies. Once we know how to label the oscillators and we know how many of them there are, then this is the way of keeping track of how many different oscillators there are. One more thing we need to know. We need to know the frequency of an oscillator, and the frequency of an oscillator, namely the oscillator that has wave number kx, ky, and kz, is just equal to k, the magnitude of k, square root of kx squared plus ky squared plus kz squared, times c, equals the square root kx squared plus ky squared plus kz squared times c. Just the magnitude of the wave vector, magnitude of the wave number, times the speed of light. That's its frequency. So now we have laid out for us all of the harmonic oscillators. We've labeled them by three integers. We know the frequency of each one. We could write it in terms of the m's if we like. And we can ask how much energy is stored in this whole thing. Classically, it's quite infinite. It's quite infinite because each oscillator has the same amount of energy. Quantum mechanically, the answer is different. Well, let's sum it all up. Let's do it. Let's really get into it, get into the thing, and calculate how much energy is in this oscillating box of radiation at a temperature T. The temperature T, where does that come from? Well, the box of photons or box of radiation could be sitting on somebody's stove, that's all. It's just heated up by whatever means it's heated up by. The walls of the box become hot, they emit radiation, they absorb radiation. The radiation comes into thermal equilibrium with the walls of the box which have been heated to some temperature. How? By emission and absorption of radiation, which of course is emission and absorption of the quanta of the oscillators here, photons. Okay, that's our theory, and let's see if we can work it out now. The energy, let's write down the energy stored in the wave which is characterized by a given wave number k. Wave number means a set of three wave numbers, kx, ky, and kz, or nx, mx, my, and mz. All right, that's equal to, now we go back to the theory of harmonic oscillators. It is omega h bar divided by e to the beta omega h bar minus 1. That was the formula for the harmonic oscillator energy as a function of frequency and as a function of temperature. That's the energy of a given oscillator, and we can write that in another way. Omega is k, the magnitude of k, times the speed of light, h bar, divided by e to the beta k c, let's see, yeah, h bar. In this formula here, k is the same thing as the magnitude of k. I don't want to try to stick too many symbols into this exponent. Minus 1, excuse me. I've just rewritten the fact that omega is equal to kc h bar, but nothing else. That's the energy of the oscillator with wave number k. How much energy is there altogether? We've got to add up all the oscillators. So the total energy is equal to the sum over all of the possible modes of oscillation. That means sum of mx, my, and mz, k, c, h bar, divided by e to the beta k, c, h bar minus 1. It's a big sum. Any questions up till now? All right, to carry on, we're going to approximate this sum by an integral. The point is that, let's look at this here. K is m pi over L. Imagine the box is very big. L is large. Large now means large by comparison with the wavelengths of light in there. If L is large, the difference between neighboring values of K is small. Neighboring values of K mean neighboring values of the wave number m. All right? What's the difference between neighboring adjacent values of Kx? Let's call it delta Kx. The difference is just pi over L. In other words, if we change m by 1 unit, K changes by pi over L. When L is large, this change in K is small. So if we think of this as a sum not over m, but as a sum over the values of K, then we're summing up a large number of numbers, each of which is a function of K, and the K's are very, very closely separated, very, very dense. Here's a function of k. It's got k in the numerator, and it's got this stuff in the denominator, and we're adding it all up. And it's just the ideal situation when L gets large to replace a sum by an integral. So let's do that. We're going to replace this by an integral over k. But before we do, we have to remember that integrals and sums are related in a particular way that involves a factor that we have to keep track of. Just abstractly, a sum over integers, mx, my, and mz, is going to be replaced by an integral dkx, dky, dkz. At the moment, I haven't told you what I'm summing, but of course what I'm going to be summing is this. But just the abstract idea of a sum is going to be replaced by the abstract idea of an integral. But an integral does mean a sum. That's what this wiggly s means. And this dkx, dky, dkz is just the volume in k space of the little cells that you're summing over. Well, each cell has a size delta kx equals pi over L, delta ky equals pi over L, and delta kz equals pi over L. A simple way to think about it is dkx, dky, dkz. Integral is replaced by sum. The volume element, dkx, dky, dkz, is replaced by delta kx, delta ky, delta kz. And so we should really write that this is equal to delta, let's call it delta 3k, which means the product of delta kx, delta ky, and delta kz. That's the way to replace sums by integrals. You can either approximate an integral by a sum or approximate a sum by an integral, but you got to keep track of this factor. Now what we have here is just a sum. If we want to convert it to an integral, we have to divide by 1 over delta k cubed. That's the right prescription, the right mathematical prescription to go from sums to integrals. And so we can write that this is approximately equal to the integral dkx, dky, let's just call it d3k, times the same integrand, kc h bar divided by e to the beta, kc h bar minus 1, but we have to put in 1 over delta k cubed. What is that? That's L cubed over pi cubed. L cubed. That's interesting. That's the volume of the box. Not too surprising. We would expect that energy being extensive, or energy being typically proportional to, I was going to say, we would expect that energy is proportional to volume at a given temperature. At a given temperature, here in this calculation is where the volume comes from. Happens to be volume over pi cubed, that number is there. So the first familiar fact is that the total energy in that box is proportional to the volume, and the rest of the integral is just the energy density. Does it, first of all, does it converge? Is it finite? Yeah, it's finite. The denominator goes to 0, or the denominator gets big when k gets large. What are we worried about? We're worried about the very short wavelength oscillations, and that means very large k. When k gets large, the denominator here gets big exponentially fast, and this integral is very convergent. So the second observation is that the total energy in the box is finite. It's extremely well cut off by this exponent, and there is not an infinite amount of energy. But let's see if we can calculate it. Let's see. So what do we have? Let's calculate it and find the final law of blackbody radiation for its energy density in any case. All right. L cubed, the energy is equal to L cubed over pi cubed integral decay. I'm not going to write the integral now. I'm going to change the integration variable. We have e to the beta k c h bar. That's a monstrosity. But we can change variables. We're integrating over k, incidentally. Right? We're integrating over the three components of k. And the k that stands down here is the magnitude of the wave vector. Okay? But if I make the change of variables, and let me now change variables from k, namely beta k c h bar. Beta, c, and h bar are just constants. Let me call that u. And of course, there are three components. There's kx, this will give ux, and same thing for y, and same thing for z. We're changing variables from k to u. And when I do so, I just have to be careful and keep track of it. So let's work it out. We have L cubed over pi cubed. What happens to the integral d cubed k? For that, we can solve for k. K is equal to u divided by beta c h bar, right? So what is dk? du over beta c h bar. So that means there's going to be a d cubed u, the three components of u, and there's going to be downstairs beta c h bar cubed. That can come outside the integral. We'll take it outside the integral in a moment. Then we have omega, or we have k c h bar. What is that? U over beta. The magnitude of u over beta. And we then have 1 divided by e to the u minus 1. That's it. That's the thing that we have. Let's take all the constants and take them on the outside. Now that we've found the answer or written the answer, let's put all the constants on the outside. By constants, I mean the things independent of u. What do we have? We have equals L cubed over pi cubed, and then there is c cubed, h bar cubed in the denominator, and beta to the fourth. Beta to the fourth power downstairs. A beta from here and 3 betas from here. And then an integral. D cubed u, I'll just write u meaning the magnitude of u, divided by e to the u minus 1. This is an integral. It's a definite integral going over positive values of the 3 components of u. Only positive values. Why? Because the original things that we started with, which were, where are they? Well, the m's. The m's were positive integers. So u is positive, and the integral is from 0 to infinity for all 3 integrals. That's it. This is a number. I'm going to tell you in a little while what this number is. This number is a famous integral, and I'll tell you what the number is. Anybody know what the number is? It's pi to the 4th over 15. No, not quite. Not that. It's not. It's 4 pi times pi to the 4. 4 pi to the 5th over 15. Some such number, some silly number. It's a definite integral. Right? You can find it in tables. It's a 3-dimensional integral. How do you make a 1-dimensional integral out of this? Right, spherical coordinates, integral 0 to infinity. Okay, go ahead. Tell me what to do next. 4 pi, right? 4 pi. 4 pi u squared, that gives you u cubed altogether, e to the u minus 1. So there's a factor of 4 pi out here. Let's put the 4 pi. And it becomes this integral. But that's not quite right. You know why it's not right? Because this integral would be integrating, it's, you went to spherical coordinates. Right? There are, in 3 dimensions, there are 8 octants. 8 octants that this integral is integrated over. But we only want the octant where all components of u are positive. So there's a factor of 1/8. Not important. I mean, there is a factor of 1/8 because we've overcounted. But that's it. That's the number. So let's put the 4 pi outside. There's an 8 downstairs. And then there is this integral of u cubed over e to the u minus 1. Famous integral. Can be written in terms of Riemann zeta functions and gamma functions and this and that. But it actually has a numerical value, and it's equal to pi to the 4th over 15. Pi to the 4th over 15. All right, almost the final answer. L cubed 4 pi, pi to the 4th over 15. My God, all these other things. 8 pi cubed, c cubed, h bar cubed, and finally 1 over beta to the 4th. That's the interesting piece here. 1 over beta to the 4th. Why? 1 over beta to the 4th. Why is 1 over beta to the 4th interesting? Because this is t to the 4th. Yeah, Stefan Boltzmann. T to the 4th. T to the 4th power. Times some number. Oh, sorry. T to the 4th times L cubed. Volume times t to the 4th. It's telling you, first of all, that the energy density in thermal radiation is proportional to t to the 4th. The total amount of energy is finite, the energy density is finite, and this coefficient here is, apart from a numerical factor like a quarter or something, is called the Stefan Boltzmann factor, the Stefan Boltzmann number, constant. Let's see, I want to write it down correctly. Oh, anybody know what's missing? There's a factor of 2 missing. Anybody know where the factor of 2 missing is? 2 polarization states of the photon, yeah. Each wave vector can support 2 distinct orthogonal kinds of oscillations. A wave vector going in a given direction can oscillate vertically. The electric field can oscillate vertically. It can oscillate horizontally. Or anywhere in between, but in between can be made up out of the horizontal and the vertical polarizations. So in fact, there's another factor of 2. No, it's just 2. Two polarization states, that's it, not 2 cubed. Okay, for each direction, there's 2 possible polarization states. All right, all of this is called, well, it's not quite the it's the standard Stefan Boltzmann constant, but it's related to it by some numerical factor and a factor of c. Let's see if I have the precise formula here. Yeah. Here's the final formula. But you know, the whole story is a long story and a complicated story. But it's really just adding up the quantum mechanical energy in each harmonic oscillator, each mode of vibration. And the important thing is this exponential downstairs, which really kills off the energy in the high-frequency oscillators. Yeah?
May I ask how far Planck got along in this?
No. Well, I don't read German, so I've never tried to read it. Yeah. Oh, yeah, certainly. Yeah. We got the whole formula. Yeah, but through what logic is a little bit unclear. Quite unclear to me. Here's the final formula. E equals volume t to the 4th, and I have pi squared over 15 C cubed H bar cubed, which I believe is also equal to the volume times T to the fourth times 4 over C times the thing which is called the Stefan-Boltzmann constant. The Stefan-Boltzmann constant is, of course, just C over 4 times this. So this is the constant that appears there. Number one, it agrees with experiment, but that was simply Planck's choice of Planck's constant. So there was no great triumph in the numerical value fitting the Stefan-Boltzmann constant. But there was something else that, that we've forgot, that sort of passed by us. Where is the cutoff in frequencies that rescues the energy from being infinite? And the answer is, if you go back to the energy stored in these harmonic oscillators, you go from classical to quantum mechanical. In other words, the suppression happens at a frequency which is related to the temperature. When h bar omega, that's the energy stored in a single quantum, is about equal to the classical energy that would be in that oscillator. All right, we can put in Boltzmann's constant if we want, a different K Boltzmann, but I'm going to leave it out. When h bar omega is about equal to the temperature, or when the temperature gets up to about a magnitude h omega, that's when that oscillator starts to begin to oscillate. When the temperature becomes high enough, that oscillator begins to oscillate. Another way of saying it is the cutoff in frequencies is omega equals the temperature over h bar. Frequencies higher than this, the energy in a single quantum is too high to be excited. So omega is equal to T over h bar. And remember what omega is. Omega is K times C. And so the wave number cutoff, let's call it cutoff, is at T over h bar divided by C? Or is it times C? Let's see. K omega is that. Omega is K times C over C. So we see another feature that, yes, it is as if the short wavelengths were cut off, but not by a cutoff which is independent of the temperature. The cutoff, this corresponds to a wavelength, 1 over a wavelength of order T over h bar C. When the wavelength is shorter than this, those oscillators can't oscillate. They have too much energy in a single quantum to be able to oscillate. And so we see here that the cutoff is temperature dependent, exactly, and what's more, exactly equal to what the experimental cutoff on frequencies was. So this was the great success. In a sense, this was the great success, that the shape of the spectrum was cut off, the classical spectrum was cut off at wave numbers equal to T over h bar C. Do I have that right? Yeah, I do. T over h bar C. Okay.
Does that mean if there was an oscillation at high frequencies, then Planck's uncertainty principle would be violated because you would know too much about the position and
Well, I would just say the energy of a single quantum is way above the classical energy. So the classical energy corresponds to a small fraction of a quantum, but you can't split quanta.
Okay.
I think that's the right way to say it.
So is there a problem with 0 point energy? Is there a problem with 0 point energy?
0 point energy is a constant, of course. It's there whether this temperature is 0 or the temperature is anything else.
And then you got all these infinite number of modes.
Right. So there is an infinity in the 0 point energy, but it's just a constant, and so it doesn't affect adding a constant. Look, this is a problem that has plagued physics for a long time. the 0-point quantum mechanical energy is not zero. Right? What does 0-point energy come into, since it's only an additive constant? Well, it comes into gravitation. Energy is the source of the gravitational field. So the question is, why isn't the vacuum, empty space gravitating? And we won't get into that now. Short of that, it really has no implication. It's just an additive constant in the energy of the world that doesn't have any effect on energy differences, if you like. So that's not to say that it's not important. I mean, it may be important, and it's important to understand why it doesn't gravitate, but that's a mystery.
It's important to understand why it's unimportant.
Yeah, it's important. Right. And this has been argued about. I think there was an argument between Dirac and Pauli. Pauli said, what about this vacuum energy? And Dirac said, it's infinite, so it can't be there. And Pauli said, just because it's infinite, that doesn't mean it's zero, and so forth and so on. And, but as far as energy differences goes, this is it. And that's good enough. All right,
The experimentalist that was measuring this, it seems like a very difficult experiment because you have to control the temperature of the vessel to maybe a few degrees, and they're working at several thousand degrees. So, did they really think that I can't imagine the experimental data being better than
I don't think the
5 or 10%.
I don't think better than what?
I can't imagine the experimental data being better than 5 or 10%.
You mean at that time?
Yeah, especially at that time.
Probably wasn't better than 5 or 10%. I don't know. These days, you can do these things highly accurately, with great accuracy. Yeah.
Another question now. This is all derived by having a volume full of radiation. But it turns out a lump of coal also has this distribution. Can you explain why? I mean, a lump of coal is pretty far from a box with reflecting size and a little hole in it. Why does a lump of coal have such a distribution?
Thermal equilibrium is thermal equilibrium. If you, first of all, we haven't talked about emission of radiation. We've just talked about the energy density inside a box. But you're right. A lump of coal, of course, is just an object which absorbs and doesn't reflect much energy. Okay. So if you take the box of radiation as we've defined it, and we put a lump of coal into it, that lump of coal will absorb and emit radiation. It will absorb and emit radiation in such a way as to come to equilibrium. It'll eventually come to equilibrium with the thermal radiation there, and that means it will be emitting as much as it's absorbing. So it's emitting as much as it's absorbing at each wavelength. At each wavelength, otherwise it would get out of equilibrium. So it's emitting and absorbing at each wavelength, and each wavelength is being kept in equilibrium. And now all you have to do is suddenly remove the box, remove the reflecting walls, and the lump of coal is emitting, but it's not absorbing because nothing's coming back. It's emitting exactly the way it was emitting before, but it's no longer absorbing. And the emission should be such that were the walls there, it would be the right amount of emission to balance and keep the system in equilibrium. But we haven't talked about emission of radiation from this box. We can. That's another subject. What is the connection? This was not the emission of radiation. This was the energy density in the radiation. Now you can ask, what does this have to do with the original Stefan Boltzmann law? The original Stefan Boltzmann law was about the luminosity, the luminosity. And what it has to do with, if you take the box, let's see how to think about this. Well, just take the surface of a hot region. The region could be the box, or it could be the box with a little pinhole in it. Radiation is bouncing off the walls. It has a certain energy density. And it doesn't bounce off the opening here. It just goes out. Goes out with the speed of light. Well, let's come back to the luminosity later. I hadn't planned to talk about it. We'll talk about it next time. What I did want to talk about was the pressure in thermal radiation. The pressure is something we can calculate by straight thermodynamics and statistical mechanics. The statistical mechanics we've already done. The luminosity is a little bit beyond what the thermodynamics can do for the simple reason that the luminosity is an out of equilibrium thing. It's radiating because it's out of equilibrium with its environment. So let's not do that now. Let's come to the pressure, which we can calculate by formulas that we've already learned. Just as an example, just as an example of the thermodynamic relations and the statistical mechanical relations, let's see if we can find the pressure. To find the pressure, let me remind you, the pressure is equal to minus the derivative of the free energy, the Helmholtz free energy, with respect to volume at fixed temperature. So we have to calculate the Helmholtz free energy. The Helmholtz free energy, A, is equal to minus the temperature times the logarithm of the partition function. So we have to calculate the partition function. Now, one way to calculate the partition function, although its logarithm, is to go back to the original oscillators and go all the ways back to the starting point and calculate Z. But there's an easier way. We've already done most of the work. And the easier way is to use the fact that the energy is equal to minus the derivative of log Z with respect to beta. You remember that? That was the energy gotten from the partition function. You calculate the log, you take the minus of it, and you differentiate it with respect to beta, and that gives you the energy. Well, we know the energy. We know the energy in terms of the temperature. Where is it? It's 4 over C sigma times VT to the 4th. 4 over sigma, that doesn't matter, not important. Over C, I think. Temperature to the 4th, which is 1 over beta to the 4th, equals minus d log Z by d beta. That's just an ordinary derivative, incidentally. I write partial derivative, but it's just a derivative. How do I calculate Z? Integrate. If we know the derivative, d log Z by d beta is equal to this, then Z, let's put the minus sign here, Z is equal to the integral d beta. Yeah, log Z, sorry, log Z. Log Z is the integral d beta of minus 4 sigma over C, 1 over beta to the 4th. Well, we can do that integral. It's just a simple integral, d beta over beta to the 4th, and it's just given by minus 4 sigma over C what's the integral of 1 over beta to the 4th? 1/3 beta to the minus 3? Yeah. 1 over beta cubed with a 1/3. Another minus sign. Okay. I've lost track of the minus sign. When I do the integral, I get a minus sign. It combines with this minus sign, I think, and I think, yeah. All right. Now we multiply by t. That gives us another 1 over beta. That's 1 over beta to the 4th. Oh, I left something out. I left something out of the formula for the energy. The volume. Another factor of volume here, huh? Volume here. Another factor of volume on the outside. Another factor of volume. Okay, now we have the free energy. This is equal to minus A. The derivative of minus A with respect to volume is the pressure at fixed temperature. So all we have to do now is differentiate this with respect to volume. That's pretty easy. The volume is just in the numerator here. And what do we find? We find that the pressure has the same numerical coefficient as the energy density, 4 sigma over C, but then an extra factor of 1/3, well, it's a t to the 4th, but then an extra factor of 1/3. That 1/3 came from doing the integral d beta over beta to the 4th. What's the result? The result is a relationship between the pressure and the energy density. There's a famous relationship. The pressure is equal to 1/3 the energy density, E over volume. You remember seeing that anywhere before? In cosmology. When we studied the radiation-dominated universe, we used pressure is equal to 1/3 the energy density. So this is a famous relationship between pressure of a radiation, and it's not a general relationship, it's a relationship for radiation. For radiation, the pressure is 1/3 the energy density. As I said, famous rule of... and so that tells you what the force on a wall, on the walls of a box is. Okay, let's see, should we stop here and get questions? That went faster than I thought it would, which may mean that I went too fast, in which case we can collect some questions now, or, yeah.
Just a forward comment, this is about the third or fourth time that, the first time was when you looked at a molecule
Yeah.
rotating and moving trends, where the same problem rose its head, that things broke down either very low temperatures or high temperatures classically, and you had to go to quantum mechanical kind of things to make it work out. Is this replicated all throughout thermodynamics as a general principle?
Yeah. I'll give you another example. The specific heat of solids. The specific heat means the relation between energy and temperature, and so it does have to do with the energy of solids. What are solids? Solids are crystals. I mean, real solids, good solids are crystals. And they vibrate, they oscillate. The crystal lattice oscillates. And so another example of this is the energy stored in a crystal lattice. Again, classical mechanics of the lattice overestimates the energy because it attributes a significant energy to every possible oscillation of this crystal lattice. But most of the oscillations, or many of the oscillations, are too high frequency so at low temperatures, classical mechanics overestimates the amount of energy stored in the thermal oscillations of a crystal lattice, and you get the wrong answer for the specific heat so yeah, it does recur over and over again. I'm not sure how many other examples of it there are. What else is there besides molecules? Solids, I suppose it also happens in liquids, although I never thought very much about it. Radiation, molecules, what else can you think of that oscillates?
Just the plain ideal gas, but you have to invoke the indistinguishable mobility of particles.
Yeah. Well, we were thinking specifically about this issue of energy stored in high-frequency oscillations. Offhand, I can't think of any other, but I'm sure there are. Yeah.
When a solid like that melts, it's got a much pressure volume change, you're adding energy. So does that mean entropy goes up a lot during that phase?
Yeah. Yeah, the entropy does go up a lot because all of a sudden the molecules are no longer locked in place and they're sort of moving randomly through the, right, certainly the entropy does go up. There's another interesting thing that you can calculate. The entropy, well, you can calculate two interesting things. We calculated the energy. We could calculate the number of photons. Let's think about the number of photons. Let's go back to the harmonic oscillator. What did we find? We found that the energy of a single harmonic oscillator was h bar omega, I think, divided by e to the beta h bar omega minus 1. Is that correct? Yeah. That's the energy. Okay. Now, each quantum of the oscillator has an energy equal to h bar omega, right? H bar omega is the energy of each quantum of oscillation. Let's use the term that we now use. H bar omega is the energy of each photon in an oscillation of the electromagnetic field. So this is the energy. If I divide it by h bar omega, it will give me the number of quanta. So let's divide it by h bar omega. The number of photons in each mode of oscillation, let's call it n omega, is e to the beta h bar omega, or minus 1. Okay? Now you can take all of the modes of oscillation and add up all of the photons. It's a similar integral. The only difference is that it doesn't have the h bar, the numerator here. Almost the identical integral, a little bit different. You can calculate the number of photons. Okay? That's not so hard to do. And you can calculate the entropy. How do we calculate the entropy? We use the statistical mechanics that we've calculated the free energy. Let's see, anybody remember the formula for relating energy, entropy, and free energy?
E minus TS.
E minus TS is, A is E minus TS, right? A is equal to E minus TS. So S is equal to E minus A divided by T. Well, we've calculated the energy. We calculated the energy, we calculated the free energy. They were proportional to each other except for a factor of 1/3, right? That's what went on here. The energy and the free energy differed by a factor of 2/3. So the energy minus the free energy is going to be basically 2/3 of something. What's it going to be? 2/3 of the energy, and the energy is proportional to T to the 4th times sigma times the Stefan-Boltzmann constant. So T to the 4th times sigma is the numerator divided by T. So T cubed times the Stefan-Boltzmann constant, or something like that, is the number of photons. Sorry, is the entropy. If you work it out, you'll find out that it's essentially equal to the number of photons, the total number of photons. The total number of photons, a numerical constant distinguishes them. This number here, if you work it out, is basically the same as the integral. Let's just look at it for a moment. Supposing I wanted to count the total number of photons. Here's the number of photons at a given frequency. It would be integral, the same integral that we did before, exactly the same integral we did before. What was it? dk kh bar what? Omega? No, omega kh bar c, e to the kh bar c minus 1 That was the integral that we did before to calculate the energy, d3k. Right? Okay. We did that integral, but now we have a different integral. It differs by not having omega in the numerator. It's exactly the same integral, except this factor is no longer there when calculating the number of photons. The result is going to be, incidentally, do you know where the 1 over beta to the fourth came from? It came from changing variables. It came from the 4 powers of k in the numerator. When we changed variables, we said that u is equal to, there's a beta here, beta h bar c times k. So in the change of variables between k and u, there are 4 powers of k in the numerator, d3k times k. That gave us a 1 over beta to the fourth. In the integral without this, we're just going to get 1 over beta cubed, which is temperature cubed. So the number of photons will be proportional to the entropy. That's a nice thing. What it says is that the total entropy at any temperature is essentially the same as the total number of photons. 1 bit of information, if you like, for each photon. It's not 1, it's some numerical number. But the entropy and the number of photons are linearly proportional to each other. So entropy in thermal equilibrium counts number of photons in the radiation. You can work that out. It's a nice integral to do. You work out the integral associated with the number of photons and compare it with the entropy, and that will give you the entropy per photon, if you like, the entropy per photon in the thermal radiation. And, you know, it's not temperature dependent. It's just some number which I don't remember. It's got pi's in it and other things. Yeah, I think it's a nasty integral. You can't do the integral, but you can express it in terms of Riemann zeta functions. But it's a number. Okay. Yes?
If you had a gas of electrons, would
Yeah.
one electron equal 1 beta?
No, not in general, no. Only at very high temperatures would that be true. Take the case of low temperatures. At very, very low temperatures, the electron gas freezes into a, not into a solid, it freezes into a, well, it freezes into a ground state, some ground state where every electron occupies its own special state because of the Pauli exclusion principle, and it has 0 entropy. So no, it is not true that that entropy is equal to the number of electrons. No, it's rather special to this system.
Because the zero state is, the zero energy is not zero in this system, you're saying?
Say it again?
Because the zero energy isn't zero in this system.
0 energy isn't 0.
Ground state.
Well, that's not the reason. That's not the reason. As you remove heat from a box of radiation, you decrease the number of photons. Right? Photons are not conserved. And cooling the box of gas just eliminates, removes photons from it. So as you cool it down towards its ground state, and eventually when you get down to very, very low temperatures, there are no photons left. So the number of photons and the entropy both go to 0 in the ground state. For a system of electrons, electrons are conserved. You start taking out the energy from them, the electrons don't go away. So if you cool a system of electrons down to 0 temperature, there's a lot of electrons but no entropy. So the entropy can't be equal to the number of electrons. But photons are not conserved, and as you cool it, the photons are just eliminated. They're absorbed into the walls. Okay. Any other questions? If not, we'll go home a little bit early.
For more, please visit us at stanford.edu.